Welcome to The Explainer. So, have you ever just stopped and stared at your phone or maybe your laptop and wondered what's actually happening beneath the glass? I mean, under all those vibrant colors, the sleek apps, the crazy complex software, there's this hidden, completely invisible mathematical language that is literally driving every single action. Well, today, we're going to demystify that hidden language. We're diving headfirst into the digital number systems that make up the absolute bedrock of modern electronics. We're going to learn exactly how we translate our everyday human numbers into machine code and then back again. It's kind of like learning to speak to the Matrix.
Okay, let's tackle this foundational problem right out of the gate. You and I, we naturally think in tens, right? We've got 10 fingers, so a base 10 or decimal system just makes intuitive sense to us. But computers, they don't have hands. They are just electronic circuits, switches, and transistors. At the absolute hardware level, a machine only understands two distinct states. Voltage is either present or it's not. It's either on or it's off. So, how in the world do we bridge that massive gap between our complex human calculations and a machine that strictly operates on this dizzying, rapid-fire logic of ones and zeros? Well, that translation is exactly what we're going to figure out.
Here is our game plan for today's explainer. First, decoding digital number systems. Second, the universal conversion key. Third, decimal to any base. Fourth, the octal and hex shortcut. And finally, binary codes in action. Let's jump into section 1, decoding digital number systems, the basics of base. Since our human-centric math desperately needs a robust translator to turn into computer-centric logic, this table beautifully illustrates the landscape we're working with. Right in the middle, we've got our familiar decimal system, base 10, using digits 0 through 9. Above it is binary, the absolute native language of computers. That's a base of 2, using literally just 0 and 1. Then there's octal, using a base of 8. But check out the bottom one, the hexadecimal system. It operates on a base of 16. Now, because we obviously run out of single-digit numbers after 9, hexadecimal actually steals the letters A through F to represent values 10 all the way up to 15. Pretty clever, right? Let's lock in a crucial piece of vocab right now. You're going to hear the term radix thrown around a lot, which is really just a fancy word for base. The radix is simply defined as the number of distinct symbols or digits used in a specific number system. Think of it as the absolute ceiling of that system. The range of values for any given digit is always from 0 up to the radix minus 1. That is exactly why base 8 octal maxes out at the digit 7, and why our base 10 decimal system stops at 9. Moving right along to section 2. The universal conversion key, any base to decimal. So now that we know what these different bases are, how do we actually translate this completely foreign machine logic back into the decimal math we know and love? We do it using this formula. Now, I know it sounds a bit technical, but I like to call it the universal key because it can literally unlock and convert any number base back to decimal. It's the polynomial formula. The rule is actually super simple. You just expand the number in a power series and then add all the terms based on the positional weight of the radix, which we call r. Basically, every single position a digit sits in carries a specific weight based entirely on the power of its base. All right, let's slow things down for a second and see this key in action with a really clear example. Let's say we want to convert the octal number 314 into decimal. Our radix, or base, is 8. Working from right to left, that digit 4 is sitting in position 0. So we multiply 4 by 8 to the power of 0, which gives us 4. The digit 1 is in position 1, so we multiply 1 by 8 to the power of 1, giving us 8. And finally, that digit 3 is in position 2. We multiply 3 by 8 squared, which is 64, giving us 192. We just add those all up, 192 plus 8 plus 4, and boom, we get 204. By using this expansion, we've successfully proven that 314 in octal is exactly 204 in decimal. It works perfectly. Now brace yourselves, because when we take this exact same formula and apply it to higher bases, the numbers just explode in size. Check out this massive number, 783,361. Believe it or not, this giant 6-digit decimal number is the exact mathematical equivalent of a super compact 5-character hexadecimal string, BF401. Because hexadecimal uses a base of 16, multiplying digits by 16 to the power of 2, 3, or 4 scales those values up incredibly fast. Okay, section 3, decimal to any base, flipping the script. We've gone from foreign bases back to decimal.
But what if we want to reverse it? How do we take our everyday decimal numbers and convert them into the specialized bases that computers actually need? To go the other way, we use a method called successive division. Think about it. If expanding a number with multiplication took us to decimal, it makes perfect mathematical sense that dividing a number takes us away from decimal. It's the exact mirror image of that universal key. We just take our decimal number, divide it by our new target radix, record the quotient, save the remainder, and just repeat that process over and over until the quotient hits 0.
Let's look at how this builds a binary number. Let's say we want to convert the decimal number 41 into base 2 binary. We start by dividing 41 by 2. The quotient is 20 and we get a remainder of 1. Then we take that 20 and divide it by 2 again. Quotient is 10, remainder is 0. 10 divided by 2 gives a quotient of 5, remainder 0. We just keep cascading down until our quotient is a solid 0. Now, here is the absolute secret to getting your final answer. You read the accumulated remainders from the bottom to the top. So, decimal 41 seamlessly becomes the binary string 101001.
Which brings us to section 4, the octal and hex shortcut, creating digital shorthand.
At this point, you might be wondering, hey, if computers only ever use binary ones and zeros, why do we even bother with octal and hex? Well, look at the unruly 24-bit binary monster on the left. Imagine trying to read, type, or debug thousands of lines of that. You would literally go cross-eyed, and human error is practically guaranteed. But on the right, we have its precise hexadecimal equivalent, 406b.f06. See, these systems aren't extra math burdens. They're brilliant, necessary shortcuts. They are designed to save software developers their sanity by making data clean, compact, and infinitely easier to process.
And guys, this brings us to the absolute magic trick of the whole explainer. Because 8 is 2 cubed and 16 is 2 to the 4th power, you can directly translate binary into these systems without ever touching decimal math. Let's take the 8-bit binary number, 10101110. To get octal, you start at the right and group the bits by threes. So 010, 101, and 110. That translates directly to 2, 5, and 6, giving us an octal of 256. For hexadecimal, group them by fours, 1010 and 1110. That translates to 10 and 14, which in hex shorthand is A and E, so hex AE. And if we used our universal key from earlier to convert that back to decimal, it's exactly 174. It is just such an elegant, direct translation across multiple systems in literal seconds.
All right, final section, section 5, binary codes in action, beyond simple math.
So it's one thing to understand all this abstract math, but digital systems are actively manipulating these exact patterns of ones and zeros to process real-world data inside the devices you are using right this second. Engineers actually build highly specialized codes to reduce errors and speed things up. For instance, there's BCD, or binary coded decimal. Because we humans love decimal, BCD uses a dedicated 4-bit sequence to represent single decimal digits, making inputs and outputs way easier for us to read. Then there's the XS3 code, which is a really clever self-complementing code. And honestly, my personal favorite, the gray code. In gray code, successive numbers differ by only one single bit from the previous number. That tiny, deliberate constraint drastically reduces hardware errors, making it a huge deal for things like analog to digital converters.
I love this quote from our source material because it really hits the nail on the head for this entire explainer. Shorter patterns of hex characters are easier to recognize than long patterns of ones and zeros. Simple, right? At the end of the day, all of these number systems, whether base 8, base 10, or base 16, they are really just the ultimate translation tools. They form a vital bridge. They take the sprawling, super efficient, but completely unreadable machine logic of binary and compress it down into formats that human beings can actually design, debug, and understand without losing our minds.
We have journeyed all the way from our everyday human decimals through the rigid, rapid-fire logic of computer binary and right into the elegant shorthand of hexadecimal. But I want to leave you with one final thought to ponder next time you look at your screen. We know for a fact that the simple binary switch of base 2, that humble 0 and 1, completely built our modern digital age. But as we stand right on the edge of quantum computing, where states can exist as 0, 1, or even both at the exact same time, what incredible new number system are we going to have to decode next? Keep exploring, keep questioning, and I will see you in the next explainer.